Okay, well, good afternoon, ladies and gentlemen. My name is Graham, G3BZV. About 5 years ago, I was standing on this very stage, you were sitting in those very seats, and I talked about something then called Es'hail-2, this idea of having a satellite, a geostationary satellite with microwave capability, and you looked at me and you thought, that guy doesn't, this is ridiculous what he's describing. You were very kind and generous and asked me some interesting questions, but I don't really think you believe me. Well, 5 years on, and here we are now with Oscar 100, Es'hail-2, not only launched and up there, but already operating. Before we go on to Oscar 100, though, I would like to make a little criticism, if I may, with an AMSAT sort of hat on. There are a large number of satellites being launched at the moment and being designed where the frequencies being used are in the amateur satellite service. Some of them at microwave frequencies, largely, I won't say as a result of Murray's encouragement, but partly as a result of Murray's encouragement that we should use higher frequencies in satellites to justify our existence. Well, there was one announced last week from Australia using 76 gigs.
Oh, right.
You read about it?
Yes.
Yeah, and there was quite a lot of pushback from the microwave community on the microwave reflector about what a silly idea it is to use 76 gigs as a downlink, and it's going to be very hard to track the frequency, and well, please be a bit more open-minded and think about the opportunities and the challenges it presents. It might not be the obvious choice, but they are using it for measurements of absorption, water absorption, and a whole load of other scintillation and stuff and things. But try and have a more positive outlook on things, and tracking antennas could be fixed, phased arrays, and you don't need the rotators. So that's my little request.
Yeah, just one thing, because I've been quite sceptical, especially when that announcement was made at the beginning of April.
Yes, I know, that's a timing issue. The 1st of April or the beginning of April, and it is from Australia, but we should be trying to support them, I think. Anyway, in the same way that you're sceptical now about that, some of you I'm sure were sceptical about Es'hail-2 ever coming to pass, but as I said, it has. It was, I think, in 2012 when AMSAT DL in Germany were approached by the Qatar Amateur Radio Society with this wacky idea to put an amateur transponder on a geostationary spacecraft. AMSAT DL originally were thinking only of a transponder like they would have put on Oscar 10 and 13 and put on 40, Oscar 40, a few hundred kilohertz wide for SSB and CW. And I think they had, again, using the word pushback, they had a bit of a pushback from the Qataris saying, well, we can do better than that. Most of our transponders are 30 megs or 32 megs wide. Why do you only want them half a megawatt wide? Why not have a wideband one? So they were encouraged to consider having two transponders, a narrowband one and a wideband one. And that's actually what we've got today, one that's nominally 250 kilohertz wide, and one that's normally 8 megs wide. So that was 2012. 2013 we went out and I was involved with some others out there in Doha, helping to develop and write the specs which they could then hand to the manufacturer and say, go make this. 2014 we were talking about it publicly, and then we've been patient for 5 years. That's the background. We obviously have to thank AMSAT DL, we have to thank the Qatar Amateur Radio Society and the former Prime Minister of Qatar, who is the President of the Qatar Amateur Radio Society, A71AU, and it's brought, or is capable, and I think it is bringing together the three of the strands that we've got in amateur radio at the moment that are growing and very bullish: the microwave area, the satellite area, and the amateur television area. And this spacecraft is bringing us all together. So that has to be something that has to be appreciated. Right, we're starting with David Bowman, G0MRF, a great radio amateur, a great builder. And he's going to start with a talk on the narrowband transponder. David.
Okay, thank you very much, Graham. And yes, 76 gigahertz. Well, we'll wait and see how that goes. So today then we're going to have a look at the narrowband transponder in this session, then following on from this the DATV transponder. But as you can see from the front page of January's RADCOM, this is quite a big deal, particularly for those organisations who are in the footprint. A bit sad that it doesn't cover America, but this is very big news for amateur radio. As Graham said, it's been a long time coming. So in the next 30 minutes or so, we'll have a quick look at some of these things. First of all, if you read the press, you'll come across various names. P4A was the original designation for a geostationary project, phase 4, geostationary, A because it's the first one. You may see that. Es'hail-2 is the name of the satellite given to it by the Es'hail-2 company in Qatar. They are a commercial operator. This is not an AMSAT satellite. This is a ride-share opportunity. So some amateur radio equipment has been bolted onto a commercial satellite costing tens, if not £100 million or so. And of course, once it's in orbit and operational, it gets an Oscar number if the operators want that. And this time, this is Oscar 100, the Q there designating that it came from the country of Qatar. So we'll have a quick look in an overview of the satellite, a look at the coverage area, the satellite footprint. We'll go on to have a pretty detailed look at the narrowband transponder, typical hardware you need to receive the satellite, equipment you need to transmit up to the satellite, and some antenna choices. And at the moment, this is such a popular project for manufacturers, the list of equipment changes on a weekly basis with more products coming out, ideas being iterated, and so we have a lot of very fast moving hardware for this particular satellite. Okay, what is it? It's a direct broadcast satellite owned by Es'hail-2 in Qatar. It carries 35 Ku-band TV transponders, 2 of which are used for amateur radio. Cost, we can only guess, but northwards of 50 million. The mass, 3 metric tons, 3,000 kilos. Launched in November by SpaceX from Cape Canaveral. Design lifetime, 15 years. And I'm sure we remember some of the AMSAT projects which haven't quite lived up to their lifetime expectations. Being a commercial project, hopefully this is going to be there for years to come. A collaborative project, as Graham said, between the Es'hail-2 company in Qatar, AMSAT DL, who wrote the specification for the transponders, but did not build them. The Mitsubishi Electric company said, thank you very much for the big pile of documentation. Don't get your soldering irons out, we'll do all that for you, which is wonderful. There are 2 transponders on board which we can use. One is narrowband, which is typically used for SSB, CW, digital modes. There's a lot of people experimenting with different things on that narrowband transponder. A couple of weeks ago, I was looking at it and I thought, I don't recognize that modulation, as you see it coming down a waterfall. And when I looked more closely and tilted my head, I saw Sierra Victor 8, Charlie Sierra, because somebody was sending Hellschreiber and you needed to go like that to read the message on the screen. So there's a lot of experimentation. The other one is an 8 megahertz wide transponder for digital amateur television. And thanks very much to Mike Willis and Charles this morning for the video feed. That was very exciting. Downlinks are on X-band, the satellite allocation, so 10, 4, 8, 9, so up above the narrowband bit, which you all know and love as microwavers. And the uplinks are on 2.4 gigahertz. Again, it's the satellite allocation, 2.4 and up. So let's put this into context. Amateur radio satellites. I'm quite excited about this, being a member of AMSAT. This is typical of an AMSAT project. Left-hand side here, Oscar 73, FunCube 1. A lot of the design of that and testing was carried out here at Martlesham in a room down in the corner. and that's been in space now since 2013. It's a CubeSat, simply a 10 by 10 by 10 cube. DC power input to that, about 3.5 watts, output power, a little less than half a watt. Ride share opportunity that's typical, although even these are infrequent. On the right-hand side, a microsatellite. This is the European Student Earth Orbiter, or Es'hail, financed by the ESA Education Office via the taxpayers of Europe. 50 kilograms, and we had a 1 kilogram payload in that, L-band up and VHF down. So that's a typical ride share opportunity. That's in orbit, and the AMSAT payload for that was switched on Friday for testing. Contrast that with Es'hail-2. This is one of the few pictures that actually exist, because obviously this is a commercial project. This was taken at Mitsubishi in Japan, and obviously before any of the coverings and thermal insulation was put on it, no solar panels on this as yet. The solar panels would stretch right the way out across this facility to the left and the right of the satellite. The solar panels on this can deliver 15 kilowatts. All right, so it's an order of magnitude and again above anything AMSAT has been involved in. Output power on these travelling wave tubes are likely to be specified at over 100 watts, although they will be run at slightly less than that. So what can we do in terms of communication? Well, this is a screenshot from NOVA representing where the horizon would be. And if you're anywhere within this footprint, from Brazil right the way across to Thailand and places like that, you can communicate with anyone else inside the footprint. So if you are inside that circle, it means the satellite is above your horizon. And remember, it doesn't move. Once you've got the antennas pointed on it, you're set to go. So there's a lot of people live in that area. Apparently it's 42% or so of the total surface of the planet.
66% of the world's population.
66% of the world population, I'm told. Okay, that's I can believe that. With Europe and China in there and India, it certainly has to be, doesn't it? So a very nice footprint. Shame about North America. So let's have a look at the narrowband transponder then in a little bit more detail. First of all, the uplink and downlink frequencies there. The uplink is on S-band. It requires right-hand circular polarization if you want to get the best possible signal into the satellite. Although I've heard a lot of people using linear panel antennas and things like that perfectly successfully. Center frequency is just above 2400. It's actually the lower edge of Wi-Fi channel 1. So the idea is that there won't be too much interference going up into space from that Wi-Fi channel. The peak of that is a little bit further up the band. 250 kilohertz wide. The downlink is on X-band. It's linear vertically polarized. Okay? And the center frequency of the transponder is there. For microwavers, you love path loss and performance. Uplink path loss there, 192 dB or so at the edge of that service area on S-band. Downlink path loss 205 at 10 gigs. The 250 kilohertz transponder passband is defined by two beacons. At the lower frequency end, you've got a CW beacon, which has probably been annoying you all morning from the foyer. It simply gives hi, this is QO100. At the upper end of the passband, you have a BPSK beacon, which is quite easily identifiable. It has a very unique sound. It sends telemetry from the satellite. So all the amateur radio operation goes on between those two limits. So even if your transmit frequency is a little bit variable, you should be able to identify those two beacons and always work in between them. The travelling wave tubes on the satellite are commercial space quality devices. The output is can be over 100 watts. The paper I saw, which came from the ITU, suggested they're about 140 watts maximum power. It's estimated that's been backed down by probably 6 dB or so to prolong their life and to reduce power consumption. But even so, you're looking at 50, 60 watts perhaps output from those travelling wave tubes on this transponder. Spacecraft antenna gain, remember it's rather like illuminating a dish. The satellite is 36,000 kilometres away from the equator. The Earth's diameter is about 13,000 kilometres, so we're looking at an object at 3 Earth diameters away. So the Earth is beginning to diminish in the distance. So you need quite high gain to illuminate that circle of the Earth that you can see. And I've seen a 17 dBi given as a figure on the paper. I've seen 20 dBi in the past as an ideal dish feed to illuminate the Earth from that distance. So it's a lot of radiated power. The specification is 31 dBW, so over a kilowatt at the edge of that footprint. And remember, as the Earth curves around, that's another few thousand kilometers further on than the bit closest to the satellite at the equator. The transponder, the narrowband transponder, is designed for 100 users, so 50 sets of people talking to each other. And if you work that out, it comes out to about 20 watts EIRP per user. Ground station is typically an antenna of less than a meter and an output power on S-band of less than 10 watts, or 10 watts or below. And I've heard lots of people on this satellite running 1 watt at the dish feed and getting quite a decent SSB signal into it. So 1 watt and a 1 meter dish works very well. There's some figures there for GT ratio. That's at the edge of the service area. And I think quite a nice one was some information given to me by Sam Jewell, G4DDK. He sat down with a circularly polarized antenna and very carefully measured that if you send 29 dBW up to the satellite, that's 800 watts, you produce a signal which is the same level as the beacon that's being sent down. And the beacons are about 30, 35 dB above the noise level. So this is really quite good. You can get away with a lot less than 800 watts ERP and still have a very good signal. Okay, so details of the electronics of the thing. Well, fortunately, being a commercial system, we have dual redundancy. So we have a couple of horn antennas on it. S-band is a horn, obviously right-hand circular polarization. The signal can be switched to one of 2 S-band receivers. So really that's S-band receive and then up conversion to 10 gigahertz, all in these little modules. And then there's 2 traveling wave tube amplifiers, but the signal can be routed to either of them. So if anything fails, then we can at least route the signals around the system so it keeps operating. The output is also a horn antenna, but this time, as opposed to being circular, it's horizontal polarization for the wideband transponder, vertical polarization for the narrowband. From the UK, usually you end up with something like this. This one's an octagon LNB. And although you look at this in your dish feed and you think, okay, well, that's vertical polarization, yeah, because the connectors are pointing down. You just think about this. In fact, from this point on the planet, you need to just skew that about 20 degrees to compensate for our geographic position. Okay, I spent about an hour trying to find the maximum signal. Couldn't find it. Then it took me 2 minutes to find the minimum, and then rotate it 90 degrees. Okay, so look for the minimum. And there's some more details at the bottom there of frequencies for the upper, center, and lower portion of the transponder. This is one you may not see very often. This is what's actually inside those blocks, those S-band receivers. We've got a broadband an S-band preamplifier going into a mixer. The mixer takes the signal down from S-band to some IF frequency, I would guess, at UHF. The UHF, from this point, is split by a hybrid. So we have the wideband transponder output here, ready to go off for processing. And then up in this direction, we have the narrowband transponder with the bandwidth defined by a SAW filter. The narrowband transponder also has AGC. The wideband does not. AGC attack time is typically fast, so 50 milliseconds attack time, 2 seconds decay. And then from then on, it gets mixed back up. And if you notice, it's a single local oscillator used for mixing down and then back up. So it goes from, let's say, UHF back up to S-band again. And then finally, something around 8 gigahertz or so, mixing up to 10 gigahertz output. So that's all in that little S-band to X-band converter. Typical of HF, that's the band plan for the narrowband transponder. It follows the typical arrangements you have on say, 20 meters, where you have SSB at the top end, CW at the bottom, and then a fairly large area in the middle now for all those wonderful exotic modes that people use, various digital modes, anything from SSTV, JT4, JT9, FT8, etc. So what do you actually need to get onto this satellite? Well, typically you'll need a dish of some sort with an LNB. Of course, there are many different solutions, and as I say, this is changing weekly with available equipment. What I've done is described at the top here. So I have a 0.6 meter dish. You may have seen it outside the main entrance, just being supported on a small tripod. It uses an LNB like this one. This is the OT LSO. They've been around for a long time. I think Andy Talbot did some great work on looking inside these a few years ago, well documented on the internet. As soon as this satellite came out, all the stocks on eBay disappeared, and they were about £14. I saw one for 149 euros the other day. Don't buy that. There's other choices. But these are quite good. Of course, they are not DRO controlled these days. These have a phase-locked loop inside them, and if you choose something, it's got to be a phase-locked version of this. Not particularly for stability, but really for phase noise. The DRO phase noise is really excessive, but something with a PLL in it has sufficiently low noise to make CW and SSB operating reasonably pleasant. They do drift. I was quite surprised when I opened this up. The performance is very high, the noise figure is very good. Pointed at the sky, nice clear screen on the waterfall. Pointed at the ground, waterfall goes hugely yellow, indicating a very strong signal sky to hot Earth. However, these are controlled by a crystal inside this. 27 megahertz, looks like an old HCU crystal from the 1970s, but with a shorter format. If you use one of those, between switch on and about 20 minutes later, it'll move 30 kilohertz, so you can have great fun chasing signals up and down the band. After that, they're reasonably tolerable, but a better choice is to either replace the crystal with a TCXO. The one I have outside has got a 0.5 ppm TCXO in from DigiKey, Connor Winfield D75. That works reasonably well. But of course, purists would have this GPS locked, maybe. And because it has two outputs, it's quite possible to use one for your signal and use the other input to feed in some sort of 27 megahertz generated signal of known reliability. Okay, so depending on your idea of what drift is unacceptable, you can modify these or in various ways. Okay, octagons, many choices. So going on from the dish, and incidentally, when I convert these, I give them a quick check. If I put the TCXO in, I can hold the LNB in my hand, point it at the satellite, and see the BPSK beacon. Okay, it's not very strong, but you can see it quite clearly on the waterfall just with the LNB. This is a big signal coming down from the satellite. So from the LNB, I go into, because I had it available, a dongle. Of course, I'm from AMSAT, so it has to be a FunCube dongle, although I don't feed it from the USB end. The output from the dongle goes into, in my case, a PC, and my software of choice is SDR Sharp, because everything else stops working after a couple of weeks, and I'm not very good with software. So I have an old version of that. But of course, SDR Console by Simon Brown. Yes. Simon Brown is very good. And there are others available which will do this very nicely.
I don't know whether you know, the latest SDR console's got a geostationary beacon thing in it, which will actually offset any drift that you've got.
Absolutely. Well, we'll take a quick look at that later, but thank you for reminding me. Yeah, the output from a standard LNB is 739 megahertz and a little bit. So you have to tune the SDR in to receive that sort of IF frequency. You can also buy LNBs that have been modified. There's a chap in Austria selling these, and he changes the crystal so that the output comes out on the 70 centimeter band. So if you have a conventional radio, as opposed to wanting to use a laptop with some software, then you can go for the second option here, a dish of some sort, modified LNB by changing the crystal, and that will give an output on the 70 centimeter band. This is wishful thinking, by the way. I don't have a 9700. And the other thing you can do is you can take the same LNB and then you can down convert with an extra little box from 739 down to 2 meters, which is quite convenient because if you want to use a conventional radio, taking the downlink to 2 meters means that you can use 70 centimeters for the uplink, and that makes getting rid of mixing products so much easier, yeah, because the unwanted products are spaced a long way away from 2.4 gigs. These PCBs, this is a project I did a couple of years ago for AMSAT UK. The PCBs are available from Luciano, Papa Tango 9 Kilo in Brazil. He'll happily sell you one of those if you want to build one yourself. Or you can get the whole thing, I think, ready-made from AMSAT DL, and that takes in 739, converts the narrowband transponder down to 2 meters, and it converts the wideband transponder up to 1200 megs or something like that, so you can feed it into a set-top box or some suitable piece of equipment, which Noel will tell us about later, I'm sure.
Luciano is actually on the stream viewing this as well at the moment, along with 94 other people, so you're reaching a wide audience. Okay,
that's that's terrific. Okay, so these are 3 popular ways of receiving the satellite. I guess over time this will all sort of coalesce and there'll be a common way of doing it, but at the moment there are huge numbers of products out there to help you get on more appearing every day. There is a forum run by AMSAT DL, and you can go on there and get sort of, if you like, minute-by-minute updates of all sorts of things that people are creating. It's really very good. Okay, so receiving. Let's go to transmitting. This is the solution I've chosen to adopt. I've got a transceiver, again, wishful thinking. I take 70 sems output from that at about 5 watts, an attenuator into this device, which is made in Taiwan. I first came across it at Friedrichshafen last year. And it takes in 70 sems, or in fact you can program the local oscillator in this via USB to do almost anything you want within reason. In my case, 77's coming in, mixed with a 1968 megahertz local oscillator, and then that comes out onto 2.4 gigs. Seems very good, does everything I want it to, and it has a little monitor output on one side so that you can remotely measure the output power from the converter. It's a DC output rather than a sample of the RF. Produces typically about 1/4 of a watt, maybe 400 milliwatts if you push it. I've seen a few people run these at a watt and then they suddenly stop working because I think the output filter in it is only rated for 1/2 a watt. But really very nice, very simple solution, and about yay big, so quite good. Then of course you have to amplify that, because you can hear that on the satellite, but you really need, you know, some nice digital mode to make it comfortable. So an amplifier, lots of those around at the moment. We've been modifying these. These are Wi-Fi boosters. We've got the part number on the next slide, I think. Wi-Fi boosters, 8 watts Wi-Fi booster. I don't know why you would want to sit next to an 8 watt 2.4 gigahertz transmitter in your front room, but believe me, these are quite good for traveling 36,000 kilometers up to the satellite. They say 8 watts. This is probably 8 Chinese watts, because I've checked the specification of the devices inside and they're rated at 2.5 watts each. Okay, so there are in fact 2 MMICs inside here. The signal has a receive preamp. It's designed to go between a router and the antenna in your house. But on transmit, it senses the incoming power and then automatically switches to solid state switches inside here. And then you get a signal going through these 2 MMICs, which can give you realistically 3.5, 4 watts, very linear, very nice performance. And that's enough to get up to the satellite with quite a decent signal. So that and a 0.8 meter dish at my location works very well. Dish feeds, you need right-hand circular polarization to go up to the satellite, which means that your dish feed has to be left-hand circular. Lots of material on these. W1GHZ online antenna handbook has a lot of details. Equally, James Miller did a lot of work on this for Oscar 40 receive, probably 15 years ago now. But these are quite good. Prices about 35 to 65 pounds. This one cost 40. I think I saw some about 38. So that's the sort of price you should be paying for an amplifier of this type. So another little bit of detail there. You can't see the one I've got, but this is the internals of the Wi-Fi amplifier. It's 12 volts in with a switch mode power supply to take it down to about 6 volts. And then you've got the 2 amplifiers here, some solid state switching, more solid state switching and output. And then this is the receive preamp up here. And this device here, if you actually short 2 pins together, pins 4 and 5, George Smart, thank you very much for that mod, works really well. It will put it into transmit only mode, which means that it doesn't chop on and off in with speech. So as you speak into the microphone, it will go on and off in its standard form. It needs +4 dBm to actually do the switching. Very annoying. Short 2 pins together, it's permanently then in transmit mode. It doesn't overheat, even though you're obviously biasing it up for transmit all the time. Another one which has been out for a few weeks now, this is an early prototype, a picture I found on the internet. SG Labs, I'm sure we've seen here in the past SG Labs transverters for 23 and 13 SEMS. They're now producing a 20 watt amplifier. Quite good, 126 euros from Bulgaria, I think they are. Designed for 24 to 28 volts supplies, 16 dB gain, 20 watts output. you don't need 20 watts output really, unless you've got a long length of cable, or possibly even more than that if it's a really long length of cable. You can turn the output, you can turn the voltage down to 13.8 and still get 4 watts out of this particular amplifier. And he's shipping lots of those out of Bulgaria at the moment. Which moves us on to a bit more of a 21st century solution, as mentioned earlier. You can do all this, which we're all familiar with, or perhaps you want to go a little bit upmarket and join the software revolution. There are 2 devices which are currently being used. This is the Adlam Pluto. It's an analog devices active learning module designed for students studying communication systems, has FPGA inside. It's designed to be used in universities and things. Nice thing about this, 2 connectors on the top. This can receive and transmit at the same time. So you can take in your 739 megahertz from the LNB. That will be processed via USB and come out from your laptop or PC as audio in the headphones. And at the same time and in the other direction, you can transmit voice, have it digitized in here, goes through to the Pluto. That will then be converted to about 1 milliwatt, so not a big signal, but usable, at 2.4 gigahertz. So a single box solution, and possibly cheaper than buying all the other bits and pieces individually. Okay? That's the Pluto. The Lime SDR is another option, and I believe that gives a higher level of output power. So I'm looking at some people in the front row. How much output power from a Lime SDR?
3 milliwatts.
3 milliwatts, okay, well, sometimes a few dB means a lot, doesn't it? Okay, so that's transmitting. This device, incidentally, is supported because all of these wonderful evaluation modules are great, aren't they? Until you get the box and think, what on earth do I do for software to run this? You know, I don't know anything about FPGAs. Fortunately, we know a man who does. Simon Brown, G4 ELI, famous for Ham Radio Deluxe and these days SDR Console, has this program which will not only deal with all of these conversions at the convenient click of a tab, but it also helps correct the drift in the LNB. What Simon has done is he looks at the beacon as it's being received, identifies that digitally. It says, okay, this is the beacon. I know where that's supposed to be. He uses that as a reference and then counteracts any drift by using a signal from the satellite as its own reference. So you can solve the drift problem simply by using that solution. Very, very, very nice indeed. Does anyone use that?
Yeah.
Yes.
Okay, well, so 1, 2, 3. Okay, so a few people already using these. Very nice indeed. Okay, so let's have a quick look at the time. Getting on, so quick look at antenna choices. This is an antenna I found in my garage 15 years later. Pulled it out from AO40 receive. I thought, I wonder if this works. Brushed off the cobwebs. Took it into Chris Bridges at Surrey Space Centre and found that it had a modest return loss of about 13 dB, but that's not too bad. The nice thing is, these are very, very forgiving on errors. So it's actually 13 dB from below 2200 to above 2450. So you can make a lot of mistakes with these, and they're fairly forgiving. I obviously didn't quite get the matching right, but it works. Works nicely. Then we have some patch antennas. These are becoming all the rage. I've seen more patch antennas for 2.4 gigahertz here than I have done in absolutely ages. This is one that used to be sold as a kit by AMSAT UK. You can assemble it for left-hand or right-hand circular. The kit's not available anymore, but it's very nice, performs very well. But there are a lot of patch designs on the internet, so if you wanted to make one, they all seem to work very well. They're very predictable. Typically, a backing plate to act as the earth, a patch cut out, the precise dimensions, and depending on the way you assemble it, left or right hand circular polarization. K3TZ is a good reference for this. And again, coming up, only a couple of slides to go now, only dual band feeds. I've been talking about separate receive and transmit. You can actually have a feed which covers both 10 gigahertz for the receive and 2.4 gigs transmit. This one is commercially available from AMSAT DL. It's a patch antenna on 2.4 and a waveguide feed on 10 gigs. This has 2 SMAs, so an SMA for each band. Our very own Mike Willis, together with Paul and PA3YFM, came up with another design. This is a homemade version, and this is an open waveguide at one end, so no probes on here or SMA connectors. This is designed to go into one of these LNBs, or one similar to this. So you cut the horn off, push the 22 millimeter diameter piece of copper pipe in, and that's your waveguide to, well, PCB transition, I guess, inside there.
I've got one here which we'll pass around, but I do want it back.
Okay. Thank you very much. Okay, so one being moved around the room there. This is available as a kit of parts from Papa Echo 3 Charlie Kilo Kilo. As soon as he makes up a batch, they're gone. I read on the forum the other day that 250 people have built these things now. I don't know where they all are. Perhaps they're being passed around rooms. I haven't seen them on the satellite yet, but hopefully there's a lot of people with good intentions. And finally, we have experimenters, including somebody who's here in the room, who from the Netherlands managed to send up 1 watt using this patch antenna. I wouldn't try SSB with it, but this will go up into the satellite with a strong enough signal to do digital modes. And Andy is quickly claiming... Okay, it's the first time I've heard of somebody operating the satellite mobile. Well, one way, okay. So 800 milliwatts to a quadrifilar helix also gets in. I guess with the digital mode, Andy?
JT4G.
JT4G.
JT9G.
Yeah. Okay. I was doing a talk at a radio club a couple of weeks ago, had a CW QSO with this chap, Delta Lima 7 November X-ray. I copied 4-element Yagi, and I said, okay, what's the dish diameter that you're feeding? He said, no, 4-element Yagi, and he sent me this picture on Twitter. So this was, again, 1 watt into a 4-element printed circuit antenna, strong enough to have a CW QSO on the satellite. It really is good. Okay, so with that, I'll say thank you very much, leave the floor to Noel, and there's some useful links on there if you want to take a pic with your phones.
There is a low-cost amplifier available for 2.4. The French did a bulk buy of PCBs, and every order they had to buy 2 PA boards to get the price down. So if you ask very nicely on one of the French reflectors, they will sell you one of their spare boards.
Okay, so a French reflector with how much power is this amplifier?
10 watts.
About 10 watts, that's ideal.
Devices are available from a certain dealer in Hong Kong, 2 for 20 quid.
Okay, that's lovely. I spent £140 on a Spectrian amplifier for 20 watts from Pyro Joe in Florida. Great guy, but obviously I didn't wait long enough to find the Chinese
They're very good, but you can blow them up.
Okay.
David, thank you very much. We're running over time, but one quick question, David, or shall we? In that case, we'll take questions at the end, but in the meantime, thank you very much. As David has said, it's moving so fast. Every day or every week there seems to be something new being developed or something being enhanced. The dual band feeds have been iterated, reiterated. There is now a lot of debate exactly where to mount them, where the focal point is, and there's stuff happening so rapidly. It's really exciting. For a satellite operator, it's really a hard spacecraft. For us, in the AMSAT world, we're used to satellites having passes of 10 or 12 or 15 minutes. So we can go into the shack, work the satellite, point the beams, point the antennas, and then go back out and join the family or whatever, or go and mow the grass or all the other things we're supposed to be doing. This spacecraft is a complete time waster because you go into the shack, you try this, you try that, and an hour or 2 or 3 have gone and it's still there. So it's absolutely wonderful.